Hello, my name is Maíra, my advisor is Regiane Oliveira, and I'm going to talk about the uniqueness of limit cycles in generalized Rayleigh system. My presentation is divided in these parts: introduction, resultant corrections, and references. And I begin talking about the importance of the system to physics, because it models diabatic chemical process through a constant area duct where the effect of heat addition or rejection is considered. This equation is called a generalized Rayleigh equation, and x is a real variable, a is a constant, and is a positive real integer. But we're going to work with the equation as a system that we obtain after a change of variables, as you can see. And an observation is that the system has already been studied by Linz-Mello input because it's a classical one-parameter family of Leonard polynomial differential system. And our main goal is to prove an analogous result using tools of the qualitative theory. And we begin first proving the proposition, this proposition. So if the norm of A is different from 2, the infinity in the Poincare disk of the Leonard differential system given before is a repeller if A is negative and an attractor if A is positive. To see this, we first need to use the compactification and to see the system in the disk. And we study the system using the charts that we obtain from the compactification. So in a few words, what we do is to take the points of the plane and see them in the sphere using the radial projection. And after, we use these charts to obtain the new expression of the system. So in U, we have this expression for the system, U2, this expression, and using these forms, we see that the system has four singularities, and in the first chart, the singularities are hyperbolic because we can do a linearization of the system, and from this we understand the local behavior of the singularities, and the points are attractors if A is positive and repellers if A is negative. But in the second chart, the singularities are degenerated, so we have to apply the blow-up technique to study them, and using the change of variables with the reparameterization of the time, the system becomes this. So after applying the blow-up technique, we can understand what happens with the singularities and the behavior of the system. In a few words, the blow-up is to explode the singularity and discover the separateness of the system in the new system after a change of variables. But the separateness are maintained after the blow-up. So we understand the behavior, the local behavior of the system. Well, after we discover what happens in the infinity of the Poincare disk, we have to study the finite part, and it's easier because the expression of the system is the same, and it has only a singularity that is hyperbolic. So we have that the region is a linear center if A is 0. If the norm of A is different from 0 and less than 2, the region is a strong focus, stable if A is positive, and stable if A is negative. If the norm of A is more than 2, the region is a hyperbolic node, stable if A is positive, and unstable if A is negative. Then, using the Poincare-Bentzel theorem, because we have a compact surface, we can understand the behavior of the general behavior of the solutions, because we know that the solutions only go to a limit cycle or a singularity, and we conclude that the system has at least one limit cycle in these conditions. But in the paper that I have already cited, the authors claim that this limit cycle is unique, but they don't really prove that because they use average theory to prove the results, and their average theory can prove that this limit cycle is unique. But first we introduce this equation that we call the Leonard equation, and we study this equation as a system again using change of variables, and we introduce this notation to call the Lipschitz functions, and if the function satisfies this, it is a Lipschitz function. So I said that to introduce this theorem that will prove that the limit cycle is unique for the Rayleigh system, because the system is a particular case of the Leonard system and satisfies the hypothesis of the theorem, and the affirmation is proved. So after the affirmation is proved, I finish my presentation, and you can see the references here to see more proofs. And thank you for the attention.